In this video, we're going to talk about momentum and force. Now, what is momentum? Now, momentum is defined as momentum equals mass times velocity. The mass of a body multiplied by the velocity of the body. Now, momentum is something somehow related to the force. Now, when you have a large momentum, that means there'll be a large force. For example, a bullet, when it's fired from a gun, moves at a very, very fast velocity. It has a very high momentum. It can penetrate a target. It can do a lot of damage. Now, momentum also depends, even though the bullet is light, okay, because of its velocity, it has a very large momentum. Now, if you have a car and a lorry, both traveling at the same speed, now which one has got a greater momentum? Obviously, the lorry is going to have a bigger momentum because it has a larger mass. And which one will require more force to stop it? Of course, it will have to be the lorry. The brakes of the lorry have to be much, much stronger to stop it because of its greater momentum. Now, Newton's law says, Newton's second law says that the rate of change of momentum is equal to the applied force. Rate of change of momentum is equal to the applied force. Okay, now we're going to derive a formula using Newton's law. Let us consider a force F acting on a body of mass m for time t. It changes the velocity of the body from u to v. Okay, a body was moving at a speed u. A force F acts on it for a certain time t and changes the velocity of the body from u to v. Okay, we can write down what is the initial momentum of the body. Momentum. So remember, momentum is mass times velocity. Mass is m. The initial velocity is u. This is m times u, or mu. Final momentum. Now, after the force acts on it, it changes velocity to v. So the final momentum after the force has acted is going to be m times v. What is the change in momentum? It's going to be final momentum minus the initial momentum, which is mv minus mu. Okay, and what's the rate of change of momentum? Of mmtm. I'm just going to write momentum as mmtm. The rate of change, now the force acts for a time t, so in this time t, the momentum will change mv minus mu divided by t. And the rate of change of momentum is equal to the applied force. According to Newton's second law of motion, this is equal to F. Okay, that's the force that we are applying. So this is the formula for the rate of change of momentum is equal to the applied force. Now, if I take m as a common factor, so we can say F is equal to, now if I take m as a common factor, inside you're left with V minus U divided by T. Now, that looks familiar. This is the change in velocity divided by time, which is the acceleration. Okay, now we already done that in the previous video. So F is equal to n. Now V minus U over T is same as acceleration, A. So we can say this is same as acceleration. So force equals mass times the acceleration. Okay, and this is the equation that gives us the definition of Newton. The force is measured in Newton. Now, if we take the mass of 1 kilogram, if the mass is 1 kilogram and acceleration is 1 meters per second squared, then the force will be 1 Newton. We say that force is 1 Newton, which accelerates a mass of 1 kilogram at a rate of 1 meters per second square. Okay, it's a force. 1 Newton is the force that gives a mass of 1 kilogram and acceleration of 1 meters per second square. Okay, now what does that mean? Now, force depends on acceleration. Okay, now when you accelerate an object, like for example, if you were going in a car at 30 miles an hour and a child runs in front of the car very quickly and you put your emergency brakes on to make the car stop very, very quickly. Now, how do you feel when you do an emergency stop? Your body gets thrown forward because your body, when the car was moving, your body was moving also at 30 miles per hour. But the car stopped suddenly, but your body, the inertia of your body makes your body continue to move, and that's why you get thrown forward. And if you weren't wearing a seatbelt, you probably your head will hit in the windscreen or the front panel of the car. Now, so when the car stops suddenly, I mean the time is very short. If the time is short, then the force will be very large. Now, if on the other hand, you are driving at 30 miles an hour and you see the traffic light change 200 meters away to red. So you brake slowly, okay, until you come to a stop at the traffic light. So here, the time taken is much longer, therefore the acceleration is much smaller, and therefore the force is also smaller. Okay, from this formula, mv minus mu equals, now if I take the t to the other side, I multiply both sides by t, you get F times t. Now this quantity, F times t, is known as the impulse. Now this is known as the impulse, and this is the change in momentum. Impulse is equal to the change in momentum. Now this is a very important equation which has implications in car safety, and we're going to discuss that. So if I write F times T equals mv minus mu. Now, this is the change in momentum. Now, suppose the change in momentum is 100 kilogram meters per second. Now, to change the momentum 100 kilometers per second, now you could have a force. Now, if the time is, if the time is, say, 1 second, okay, if that momentum changes very, very quickly, all right, let's say if the time is 10 seconds. Now, if the time is 10, now to get this 100, you've got, the force must be 10 times 10 will make 100. So force must be 10. 10 times 10. So if the time is 10 seconds, the force is 10 Newton. Okay, that's a small force because it's taking a long time. Now, however, if you try to change the momentum very, very quickly, to stop something very quickly, say if the t equals 2 seconds, then what is the force going to be? Now, if the t is 2 seconds, if this is 2 times what makes 100? 2 times 50 will make 100. That means the force has gone up to 50 Newton. So, now you can see as the time of collision is short time of collision means very large force. A long time of collision means a smaller force. Implies large force. Okay, when you have a long time, it's a small force. Now, we know that seat belts in a car, okay, no, seat belts are designed to stretch in a collision. Car safety. Okay, let's talk about car safety. Now, we say, number one, seat belts are designed to stretch in a collision. Okay, why is that? When we're wearing seat belts, when a crash happens, okay, your body moves forward, and the seat belts, they stretch a little bit to absorb the shock. Okay, now this is to make the time of collision much longer, so the force acting on the person is smaller. Now, can you imagine if the seatbelt was made of rigid steel and you hit a brick wall at 30 miles an hour? What's going to happen to you? When your body stops abruptly, the seat belt will break all the ribs in your body. Okay, if it didn't stretch, because the force will be very large, because the steel doesn't stretch. Now, the second thing is there is the crumple zones in a car, okay, which absorb the shock. Okay, what is crumple zone? No, the front of the car is designed so that in a collision, it collapses inwards, okay, to make the time of collision longer, so the force acting on the driver will be less. So this is what we mean by the crumple zone. The crumple zone is the front of the car is usually designed to collapse inward slowly. Okay. Now, if it was rigid, then in a collision, the car will stop abruptly, very quickly, in a short time. There will be a very large force acting on the driver, and the driver might go flying out of the windscreen. Okay, so this is the very important for car safety. Now, why is it that when you kick a stone, it will hurt your foot, but if you kick a ball, it doesn't? Well, the reason is because the stone is rigid, okay, and when your foot impacts with the stone, the time of impact is very, very short. Therefore, a very large force acts on you, which will hurt your foot. Now, the ball, on the other hand, is elastic. It goes inwards. It makes the time of collision longer. Okay, a ball. When you kick a ball, you see, like if this is your foot coming to kick the ball bends inwards like that. Okay, to make the time of collision longer. So therefore, there'll be less force acting on you. So we'll finish this video here, otherwise it'll get too long. We'll talk about the conservation of momentum in the next video.